Okay, so recording is started now, and first of all, I would like to welcome you all peoples in this session of plasma physics. I hope all of you are doing well. Your health is very good, and this is very good morning, and hope it will continue till our lecture ends. So, very good morning to all of you. Before we start, let me tell you the plan of our talk. Initially, I will explain the part which we have discussed so far, the topics which we have discussed so far, and then I will we will just revise the thing as per my previous talk. Means in our previous lecture, we have decided that in today's lecture we will just will just revise the concept one by one, one by one. You peoples will see the things, will tell me the particular slide, about that particular slide, how things are derived in that particular slide, that you will tell me, and based on that we are going to discuss the things. Okay, so let's move forward and let's see what we have discussed so far. So far we have discussed the topics, and the thing which we are discussing is the RF conductivity. And after discussing the topics are there, we discussed some species which remain present within plasma and their associated quantities. How we consider these quantities in plasma, that part we have discussed. Density, charge, mass, drift velocity. These are the things which remain present in plasma. Are you getting my voice? My voice is clear?
Yes, sir.
Okay, I think it should not break in between, because network connectivity is fast. Not facing any network issue right now. That means the connectivity should go fast. Okay, now then temperature, and then we started discussing equation of motion. And in equation of motion, we use Newton's second law, and by taking that second law as a base, we derived our equation of motion, in which we consider certain forces like electrical force, magnetic force, collisional rate force, pressure gradient force, and if needed, gravitational force should be also considered. The part we have seen, so we have derived this relation in two parts. Considering force, we have identified different forces, and we identified the motion also, dv by dt we analyze, and what should be the form of dv by dt we should consider, that we have seen, and that part we had included. And considering them, the final version of equation of motion that we had obtained was this, sorry, this, in which this is the motion, change in motion, you can say, with respect to time as well as space. And this shows the different forces which changes motion of the, if the any particular entity or any particular charge particle which remain present in the plasma. So this is how we have derived the equation of motion, and then we consider the equation of continuity. And the relation which we had obtained was this equation of continuity. Then we have seen Maxwell's equation in plasma, how, what should be the form of Maxwell's equation that we should consider in plasma. So that part we have discussed. Then we have discussed collisions, and we have derived relation for the collision, considering the space up to which a charged particle may face force due to any ion. And the version of the collisional frequency which we have observed, the particular equation which we have obtained was this: we knew is equal to niqvth, where q is the cross sectional area, and vth is the thermal velocity. And if we put the value of t instead of vth, this is the form which we have obtained, where we have identified the relation between nu and v and t. And using that relation, we have discussed many things. And then we decided discuss the linearization of equation of motion. So this part we have seen, just uh, to identify the DC conductivity, to calculate the DC conductivity. This part is necessary to discuss. And that's why we had taken this part first, linearization of equation of motion, where we have identified the value of v after linearization. And then by understanding the DC conductivity, we define the sigma also, how conductivity is there and current density is there when DC field is applied, DC electric field is applied. So this part we have discussed so far. And then we discussed one important phenomena called gun oscillation, which we observed in gallium arsenide. And this particular material is generally considered as the material which shows solid state plasma. So this shows solid state plasma property in material. So this diode show property something like this. If DC current is applied, it should be observed by us. But at high electric field, it shows this particular property where we observe this type of spikes in the electric current, or you can say the flow of current. Somewhere electric field current goes very high and then goes down. This particular thing we have observed in these type of materials. And to understand this and to explain this, he has given this particular explanation where he observed that if we increase electric field of this type of material at certain point, the current density start to decrease, and a negative decrement region we observe, and that region is considered as the negative differential conductivity region. So this part we have explained. Why it is observed. So the reason is when electron goes from valence band to conduction band, their effective mass changes, and due to this relation, due to the change in effective mass, here you can see J should, due to increment in M, J should decrease, and that's why we are observing this decrement in the current. And then the use of relations, we derive different relation. We have derived the equation for the growth period is the relation we had derived. And then we had started discussing the plasma response to radio frequency. So as I told you, this part we'll discuss today. And you peoples, I will just speak the name of any of the person who is present in this meeting, and will explain this particular slide. So what is there, you have to explain only what is there in this slide and what we have derived within this slide. So at the end of this slide, which particular equation we have derived and uh, what is its relation, that you have to share. So let's start from this slide only. Okay. So who will tell me what is there? Let me speak the name. In my list, Ankit is first. Ankit, what is here?
Hello.
Yes.
Yeah. So this slide shows that the generation of the plasma in the AC field and the radio frequency field. So
Good.
we can see that in the middle one there is a one vacuum tube. Uh,
Yes. Good.
in the first figure we can say that in the middle one there is a one vacuum tube, and there are two electrodes connected at the end of the this vacuum tube, and the
Good.
vacuum are created in the tube, and the low pressure gas is filled in the tube,
Good.
and when we applied the field to the these electrodes,
Good.
or a connect field to the these electrodes, the
Good.
gas in the vacuum tube is going to the gas discharge, and the generation of plasma, and plasma is generated. In the below figure,
Good.
we apply the radio frequency field, which means it is simply a electric field or magnetic field, but it is in the range of the radio frequency. or it
Good.
is near between kilohertz to gigahertz frequency range.
Good.
And, this coil is rounded rounded in outside the vacuum tube, and when we
Good.
applied the field radio frequency field to the this coil, the passing passing current from the this coil generate a time varying magnetic field, and due to
Good.
this the generation of plasma occur in the vacuum tube, right?
Good. Nice. Nice.
Okay.
Okay, let me explain a few things here. Here again with AC, here definitely AC field we are applying, but again it can be RF, means in RF range. So that can we can apply through this. And here, Kit, it is not round. You should use word wound, 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 wound. Okay, the coil is wound. Like we use wind word for winding, showing the winding. We are winding anything over that. So the coil is wound. In that way we are saying. Okay, so nice, Ankit, very good. And with this he has explained that here in this case either we are applying through electrodes, we are applying DC electric field or AC electric field, and that AC can be in RF range also. And here through magnetic field we are applying the field over this plasma, and that field is again in RF range, and that magnetic field is applied through this solenoid which is wound around this particular tube. So very nice. Let's move forward, and let's see our next slide. Here we have explained electric field. Let me ask question to Chalak. Chalak, what is the form of field we have used? Okay. So simply try to write. It is a cos omega t. Later on, we have used this particular function. So just try to write. Can we consider this particular function is a replacement of this? And if it is so, then try to simplify the reason only. For which purpose we are doing so? For mathematical easiness, to get the mathematical advantage, or uh, to just change the function? For which purpose we have used this function rather using this particular function for the electric field? You can write in chat box, Chalak. So try to write in chat box and try to say. Okay. To get the advantage of mathematical function, means we get mathematical advantage later on. Let me explain this part later on. We just want to make a function in a way that just by differentiating this function we get the same function again and some particular multiplication factor, and in that way if we are getting same thing, then we can replace this differential function, differential operation or operator, with this algebraic operator. And to do that we have used this rather this one, because if we differentiate this one it gives a sine function which is completely different from this, but this gives this particular type of function which gives advantage for us, which gives mathematical advantage to us, and for that purpose we have done this thing. So the function electric field which we have used is a cos omega t, but here we are using this particular function because this function is same as this one, real part of a e raised to I omega t. If we take I omega t, if we take this same, and that's why. But the advantage is this: if we differentiate this one, it gives us sine omega t. But if we differentiate this one, it gives us minus I omega e raised to minus I omega t. And because of that, I can say del by del t can be replaced by I omega So in this way, to do this, we have changed our function. We have used this particular function. Later on, we are using this also. In our previous lecture, we have used same thing. So that part is here. So as I have told you, to get this advantage, we have used this function. Now here, again, using this particular function, now we are trying to replace this particular function electric field, and then because of the application of this particular function, what advantage we are getting, what changes we are getting, that we want to understand. So this is the form of uh, uh, the equation of motion for the plasma. So let me pick one person. Aparajita. Aparajita, you tell me what is there in this slide, from where we have considered time, and why this particular function is there, and when we'll just go in the next slide, or you can say when I will expand this function, when we uh, go to the next step, what is going to happen, or which particular term will just minimize or will get vanished. Aprajita, are you there? Okay, then please try to speak. Just in simple manner. I don't want the, means you don't need to speak too many words or in detail. Just simply you have to say which forces we have included here. Okay, you can write also. Okay, nice. Good. According to Aprajita, magnetic and pressure gradient forces are absent here. Very good. And that's why that terms are not considered. Only two things you can see in this equation. One is the electrical field or force due to electric field, and second is the force due to uh, collisional drag force. And the gravitational force is also absent. Very good. Now what is going to happen with this change in motion? Among these two terms, which one will get vanished? Are you there, Aparajita? This equation represents the net force as divergence of V is 0. Good. So here this part, divergence of V will be 0, because here we have considered that the field is uniform. Very good, Aparajita. Because of we have considered that the field is uniform within plasma, then it should not change, velocity should not change with space, or you can say with change in position. And that's why here, due to the positional change, velocity change should not be observed. Only with respect to change in time, with this velocity change should be observed. And that's why this term is absent here, and the equation which we have obtained is this equation in which we have dv by dt and v, sorry, nu v, which is equal to minus e, capital E upon m. We have taken the collisional drag force over this side of the equation. So this is what we are getting, and then multiplying it with e raised to mu t, the term which we are obtaining is this particular term. So who will tell me how we have obtained this one? Because I just want the answer in only one sentence. Yes, yes, Paras.
Because sir, we want to reduce the step, reduce the okay, reduce the two function into one, and we use the integration factor e raised to mu t, and in the using the e raised to vt equation, we form two two function into one function, and
It
simplicity.
reduces two terms into
Ah,
one term. Okay.
one term.
So here actually what we need to do, our aim is to reduce this part. Here we just want to club both of them, and to club them we have multiplied this with means this all equation with e raised to nu t. If I multiply this equation with e raised to nu t, both of the side with e raised to nu t, then here equation becomes dv by dt e raised to nu t plus v, sorry, nu v into e raised to nu t, which is equal to minus e, capital E upon m, e raised to nu t. This we can get. So this part if we see, then multiplying with e raised to nu t, the version or the equation which we get is nothing but the d by dt of this particular term v e raised to nu t. So means it is just expansion of this term. So by clubbing them, or you can say if I club them, then we are getting, we can write as a replacement of the two terms, I can write this one term, that is del by del t v e raised to nu t, which is equal to, this term remains as it is, e by m, capital E multiplied by s to nu t. So this is how we have obtained this one, and this we have obtained just to make our integration easier. We can integrate this part very easily, and that's why we just need to integrate this part, because if I integrate this part with respect to time, it gives me v e raised to nu t, and that's why we just need to integrate. That's why to make this integration easier, we have done this thing. And by putting the value of e here, that is a e raised to minus I omega t, and we have already e raised to nu t, and integrating them, the equation which we obtain is this one. Are you getting me? Okay, so now let me pick one more person. Let me Vatsal. Now I think start describing the remaining part of this particular equation. I will continue changing the slide. So let me make the full slide here. So how we have obtained these steps? Just describe this thing.
Just a second.
Yes.
So, in order to club those equations, we have just integrated them.
Yes.
So, after integrating, what we obtain is v e raised to mu t is equals to minus e by m integral a e raised to minus I omega t1 e raised to vt1 dt1 plus c1. We need to understand that over time we are integrating this and putting the limit t. So, the variable thing would change in this, and due to that v at a time t will depend on electric field only, because that is independent of time in this case.
Good.
So if we integrate it, it becomes minus e a e raised to I omega t e raised to mu t upon m v minus I omega plus c1.
Good.
Now,
It's
if we
new.
see this equation. The
M
exponential
multiplied by, yes, yes, go on,
the
nice.
exponential factor on the LHS can be taken on the RHS after we divide these equations. So V is also described as V is equals to minus E raised to A. Sorry. V can be described as V is equals to minus EA
E raised to,
raised to I omega t upon M V minus I omega plus C1 e raised to minus Vt. We know that C1 has to be evaluated keeping in mind the conditions at the border, conditions at the boundary. So we make an assumption that our field has just started at zero time, means t is equals to zero, where we had drift velocity also to be zero. So if we assume that, what turns out is that C1 can be written as C1 is equals to EA m upon V minus I omega. We know that C1 is a vector quantity. So we should have vector sign wherever we use C1. And if we put that back in the prior equations, the velocity of electrons can also be written as V as a function of t. And in that, we are using the complex notation EA upon mv minus I omega e raised to I omega t minus e raised to vt.
nice.
Here,
Okay.
okay.
Okay, so this is what we have derived. One thing I need to say, I know you peoples are not confused between nu and v. You know very well what is nu and what is v and what is the difference between them. But try to use this word whenever you are remembering that thing also. This one is new, it is not v. It will not change your concept definitely. For sake of speaking, for means writing, you can definitely say v. But what happens in examination, if you are recalling this quantity and somehow if you are writing new instead of v, and if you are getting confused in between at the time of writing your answer, it will just make confusion in your mind, and you will not be able to write your answer completely. So uh, try to remember this quantity as new only. Try to use the word new only for whenever you are recalling this quantity. Okay, definitely I know you are not confused between nu and v. You know this is collisional frequency and v is the velocity. But what happens in examination, whenever we are writing instead of nu, if we are writing v, then somewhere and sometimes when both of the quantities are remain present in equation, like you can see here v is also there, nu is also there. So at that time it creates confusion, and at that time we get stuck somewhere. Okay, so because of that reason, try to remember this as new only, and use this for this use word v only. Okay, are you getting me?
Okay, sir.
It is not for understanding. Definitely you are understanding very well. Whatever you have said is completely correct. Whatever, definitely you are just using word v instead of new, and it is not making any logical difference in your mind. But whenever you are writing answer, at the time of writing your answer, it will definitely create confusion in your mind in examination, because that is the time at which we are writing too many things at a time. We have to write and we have to recall too many things at a time, and instantaneously we have to write so many things. And that's why if everything is clear, if we are using proper word, if we have channelized our mind in a proper way, then your flow will not get broken. For that purpose only I am saying this. Otherwise, whatever you have said is fine, it is correct, there is nothing wrong. But try to keep this thing in your mind. Okay, because I have seen many of you people using word v for this new. Definitely, I know you peoples don't have confusion between V and nu, but if you remember them like this, it will create confusion at the time of exam. That for that purpose only I am saying this. Okay. So nice, Vatsal. Thank you. Let's go forward and let's give chance to, okay, this part I don't know whether, yes, we have discussed this thing also. Okay, so here let me explain only. Here what we have used is whenever the quantity means whenever time passes and whenever we'll reach at a time very greater than equals to 0 at very large time, this term will get vanished, and the term which we'll obtain is only this one. Okay, so this term will get vanished at a larger time. So our equation of velocity becomes something like this at a larger time. That will be let me write, okay, it's not written here, but it becomes v is equal to, yes, it is written here, e capital E divided by m nu minus I omega. So this will be the value of v as a function of time again, will obtain at a larger time. Okay, so this will happen. So this, and this way we have modified our equation. And now, by considering the steady state also, and by considering the equation of motion also, we can obtain same thing. So, Krishnaras, I think I should give you a chance to say about this, how we have obtained same value of v by using this particular function, equation of motion. Are you there, Krishnaras? Slide is there in front of you. We just have to speak how we have obtained step after steps.
Sir, for the steady state, here the some forces are absent, so we can express the equation of motion. Right? M dv by dt is equal to minus E minus M mu into V. So there are
Good.
some alien forces and some magnetic forces are which are absent. So we can express the motion equation of motion like this. This is shows as momentum loss per second via collision.
Good.
And here the electric field is time dependent,
Mm.
and also it is time
Motion.
dependent. It is not space dependent.
Good.
So we can express electric field E is equal to A E raised to minus I omega t.
Good.
And we also know that as previously we do that if we take a differentiation of E raised to minus I omega t, so then we get del upon del t is equal to minus I omega.
Good.
It
Good.
is same
And
as
wherever this dependence is there, we can use same thing everywhere. Whenever we have dependence on electric field. So here our motion is dependent on electric field. We can use that thing here also. Nice. Okay, go forward. Yes. Let me change the slide. Okay. Go ahead, Krishnaraj.
So as previous equation, we just take a right side equation m mu into v. We just take it left side, and this equation is become minus I omega m mu plus m mu into v is equal to minus e into e.
Good.
Now we take now we are we are going to subject the v. So if we take mu as a subject, then whole term we get whole term is going into the right side, and we get minus E upon m v minus I omega.
It's new. Krishnaraj, this is new and this is v. This is velocity v and this is new.
Okay, okay. Sorry, sir.
Yes. Nice. Now here we have this particular equation of for what purpose we are using this equation. J is equal to, its equation of,
Current
what is
density.
J? Current density. Very good. Now if we use this equation, current density, equation of current density, and here uh, we should put the value of v from this particular equation. If we put the value of v here, what we get? This term j is equal to n square upon m nu minus I omega into e. This term we get if we put the value of uh, v here. Okay, now go forward, Krishnaraj. Now we have obtained the value of sigma.
Value of
Say,
v, we get j is equal to n e square upon m minus I omega d. There is called conductivity. And we can also express j is equal to sigma into c. This is also equation of conductivity. So we get the sigma is equal to we know the value of j, and we put it here, then we get sigma is equal to n e square upon m minus I omega. It is called RF conductivity or radio conductivity of AC conductivity of plasma.
very good, very good. So this is how we have obtained the RF conductivity of the plasma, or you can say AC conductivity of the plasma. If we consider electric field is in the IF range, then it is considered as AC conductivity, and it is also considered as the RF conductivity. So this is equation of the RF conductivity that we have obtained in our previous lecture. So before we go forward, before we move forward, if you have any doubt, you can ask here. All of you have revised full concept. Very good to all of you, and you have done very good job. So I just like to congratulate you people that you are doing very well. You are learning these particular concepts very well according to my you can say uh, my wish, and according to my need also, you can say you are learning that particular concept. Whatever I am assuming, you are doing according to that. So very good and fine. But before we move forward, if you have any doubt, you can ask here. Gopi, if you have any doubt, you can ask here. Are you understanding all the parts whatever we are discussing here, Gopi? Okay, she is not having doubt. She is understanding all the parts very well. Thank you, Gopi. Okay, let's move forward and let's discuss the next part of this particular equation. Now here, as we know, our electric field is a complex quantity. In this particular case, if we put the E, this is our complex quantity. This particular term, if I consider, this is complex part because our E is a e raised to minus I omega t, which is a complex term. And that particular complex term we don't need to consider, because as per our assumption and as per our need and as per the particular function we have chosen, it is considered that we need to consider the real part of that particular field. So here, whenever we are taking sigma e, then we should consider real part of sigma e, because the j whatever we get should be real. It should be actual quantity, and that's why here some we should keep in our mind that the quantity which we consider here should be real, and to make it real we should consider the real part of this term sigma a. That means we should consider the real part of this particular, putting the value of e, what we get, e and sigma what we get is, as we know, sigma is n e square upon m nu square upon omega square 1 by 2 e raised to minus I5. Why I have obtained this particular term, let me explain this thing. But here, this is our sigma, and if we convert this part into real quantity, how it is converted, that I am going to show you. But when we convert it into real part, then the thing which we obtain is this one. So how we have converted this in real part? So if we have any complex number plus iv, as we have in our previous case, so or minus iv, we can write that as a square plus b square raised to 1 by 2, that we have done here, multiplied by e raised to minus I5. Doing so, that particular complex part can be written in different form, where here we need to remember that the phi is tan inverse of the imaginary part upon the real part. So tan inverse omega upon nu if we take, because our omega is the imaginary part and nu is the real part. So if we take tan inverse of omega upon nu, then this is equal to the phi. And putting the value of phi here, we can convert this particular function in this particular way, and its real part will give us the exact value of j. So what we have done, we have changed the form. As you know, we have equation in this particular form, that is nu minus I omega. So this part is imaginary, this part is real. And if we have this particular part, then we can multiply it, means we can write it like a square plus b square, considering this as b, considering this as a, or this one is a and b. We can simply write a square plus b square multiplied by e raised to I phi, where phi is tan inverse of the imaginary part upon real part. And doing so, what we are obtaining is this one. That's why it is written like this: nu square plus omega square s square plus b square nu square plus omega square raised to 1 by 2 e raised to minus I phi, where phi is tan inverse of imaginary and real part. So tan inverse of imaginary upon real part, if we say, then it is tan inverse of omega upon nu we are getting. So this is what we obtain. This is just simple conversion of this particular imaginary or complex part, just to make this function simply simpler. We are doing so, and it's a mathematical conversion only. So we can do this. That's why we have written in this way. And if we are writing like this, then the equation j which we are getting is n e square a upon m nu square plus omega square raised to 1 by 2 e raised to minus I omega t minus phi. And this gives us very important thing. And if we take the real part of it, then it get converted into n e square a cos omega t minus 5, because the way with which we have taken e raised to minus I omega t is a replacement of cos omega t. Now we are replacing this as the cos. Right now, the thing which we did previously, same thing we are doing right now. And for that purpose only, we have changed our equation in that way. So if I convert this particular function into real part, it gives us this one. Okay, definitely they are not exactly equal. Are you getting me? Are you understanding my point? This is not explicitly equal to these two. They are not right. But why we can write this is, we know we need the real part of j, and to get the real part of j, initially I think you would be knowing that we have taken e raised to omega t minus sorry, e raised to I omega t. So we considered e raised to I omega t is equal to cos omega t. That part we have considered. So same thing we are doing. What we are doing now, we are considering e raised to minus, say this is one particular function x is there. So we are considering this x as the cos. So converting this, the real part of this will be cos omega t minus phi. And that's why considering that part only, what we can write, cos omega t minus phi. So again, what we did previously, just reverting that thing, we get this function which is a real function. All the values are real, and in that way we get the real value of the current density, that is n e square a cos omega t minus phi upon m nu square plus omega square raised to 1 by 2. And here this is nothing but the phi, which shows the phase or phase difference. So here there is a phase difference between electric field, which is cos omega t, and the current density, which is cos omega t minus phi. So here in current density, this phase difference we are observing. So there is a difference of phase between the current and the electric field which we have applied. So this difference of phase remain present in this equation, and that's why it is written like this. Now, if we can measure the phase difference between current and the electric field that we apply, then the form there you can measure the collision frequency, because phi which we can measure experimentally, and omega we can be deduced. So with example, we're going to see this thing. So definitely we can identify the difference of phase also experimentally if we know the value of omega and the nu. If we have the value of omega and nu, then we can identify the phase difference also. Or if we have the phase difference, then we can identify the value of omega and nu also. This is possible through this equation, we can say. Based on that, numericals can be also asked, but right now we are not considering those numericals. But with example, we'll see why and how this is possible. So we are taking, before we take this example, if you have any doubt, you can simply ask here. Let me revise what we have done so far. Are you getting what we have done here? What should be our J? Our E is complex term or a real term? Any of you, please give the answer. In this equation, we have derived the value of sigma. You can see here it is m nu minus I omega. So this is complex. Our E is also complex. So our J in this particular way, if both of the quantities are complex, then that J will be complex or real form or real part. It will be complex or real number. It should be a real quantity, but it is actually real or complex. Paras, am I connected? Paras? Hello? Are you getting my voice?
Yes, sir.
Okay.
Yes, sir.
J is
Hello.
okay.
Yes, sir. Ave.
Nice, nice. Okay. Okay. So copy is written. J is a complex quantity. Very nice copy. So J is a complex quantity because of so C is complex and E is complex. So it should be it gives us complex value. So but we need the actual number, the real quantity. J should be real quantity. We need means our solution should be in a way that J should be real. And to convert it the real part, we should write real sigma I. And to get that real part, what we are doing is we are just writing the denominator in different way, and which is mathematically true also, that can be written mathematically. So we are not going into detail why it is so, but in mathematics we can do this thing. If we have two quantities, if we have something like a complex number plus I v and or I omega or any particular number multiple of I, if we have, then we can simply write as a square plus b square raised to 1 by 2 multiplied by e raised to minus I by this we can write, and that is what we have. We have nu minus I omega. So considering nu is a and omega is b, what I can write is a square plus b square raised to 1 by 2 e raised to minus I 5. Now here 5 should be 10 inverse of the imaginary part divided by the real part. So if I do so, imaginary part over imaginary part is omega and real part is, or the multiple of the imaginary side is omega and multiple on the real side is nu. So I can write omega upon nu here, that will be our 5. 5 is equal to 10 inverse omega upon nu. So this way I can write, and that I have written here. That is same thing is there, but in different form. So that is nu square plus omega square raised to 1 by 2 e raised to minus I 5 we have written. Why we are doing so? Because we want to consider, we want to get the real part of J. That's why we are doing this. And doing this, what we are obtaining is n e square a upon uh, nu square plus omega square raised to 1 by 2, and here we get e raised to minus I omega t. And if we take this side on this particular side, or in numerator, then it becomes plus I5. and that's why now I can write this term here, n e square a upon m v square plus omega square is to 1 by 2 mu square plus omega square is to 1 by 2 e raised to minus I omega t minus phi. And here, as we have considered previously, e raised to I omega t is nothing but its real part can be said as or can be written as cos omega t. But here multiple of I is omega t minus phi. So our cos will be cos omega t minus phi. So the real part of this equation can be written as n e square a cos omega t minus phi upon m with nu square plus omega square is to 1 by 2. So this is what we get from this particular equation. And with this, we get the real value of j. And here in this equation, we can get the value of omega t or nu if other quantities are available. For that, you are given one example. Suppose a plasma, for instance, has a phase difference of say pi by 3 between current density j and electric field E at frequency omega upon 2 pi is equal to 1 megahertz. Omega upon 2 pi we are considering as the frequency, and that we have 1 megahertz. So at this frequency, uh, suppose a plasma, for instance, is plasma difference of pi by 3 between current density, means phase difference between current density and electric field is pi by 3 at frequency omega upon 2 pi is equal to 1 megahertz. Then suppose I apply RF field of 1 megahertz to plasma and measure phase difference E, then putting the value of phi here, the value which we get is tan inverse of omega upon nu is equal to pi by 3 that we get. So nu omega is equal to nu 10 pi by 3, and 10 pi by 3 is root of 3. So the answer which we get is nu is equal to 2 pi into 10 raised to 6 upon root 3. So here we have considered uh, omega is equal to 2 pi into 10 raised to 6. Here normally whenever we are taking or whenever we are given the frequency, generally we are given angular frequency. Most of the times we are using angular frequency in our relation. I think you know the difference between the angular frequency and the actual frequency. Do you have any idea, or I should discuss that part here? This is actually this particular thing is in the form of angular frequency. Means if I take this omega, then here the value which we have kept is angular frequency, the form of angular frequency in the form of angular frequency. Do you know the difference between them? Are you there? Paras, am I connected? Okay, I think you know the difference.
Yes, sir,
But
you
let
are
me.
connected.
Okay, so let me just say in very simple word, angular frequency is frequency in terms of, you can say, certain radians, or you can say when we consider full circle or full cycle, then in terms of cycles when we consider any frequency, it is means in numbers when we get it is in the form of frequency, or we use word frequency. And when we say angular frequency, then it is observed in certain numbers of radians or per second, whatever number of radians we are observing. That is what we say angular frequency. And here we are using frequency in the angular frequency form. We are using angular frequency is omega, and putting these values we get is 2 pi into 10 raised to 6 multiplied by root 3. So this is the value of nu which we are obtaining based on the value of phase and the angular frequency. So this type of question can be asked in your examination. So keep this thing in your mind. So with this, now our unit is over. We have completed our second unit with this particular discussion, and from next lecture we'll start our next unit. So thank you so much for connecting in this particular lecture. and being present here. I think the things whatever we have discussed is clear to you. If there are any doubts, you can ask here. If there are no doubts, simply write no in the chat box so that we can conclude this session and we can end the meeting. Okay, Krishna Raj has written, thanks, sir. Okay, Krishna Raj, thank you. Okay, Vatsal is also writing, thank you. So thank you so much. I think no doubts there. So thank you so much for being connected here, and hope all of the things whatever we have discussed so far are clear to you. If you are having any doubt, you can ask in our next lecture also. And in our next lecture, we are starting our new unit, unit number 3, in which we'll discuss the propagation of waves in plasmas. So how that thing is there, how propagation is considered in plasma, that part we are going to discuss. So till that, have a nice day and do good in your studies. Thank you.